It isn't just electronegativity, though. Shape factors in, which is where our valence structure comes from. A C double bond O is massively one-sided. There is a very large partial negative and a very large partial positive. But if I have a second double bond, well, that's happening in both directions. So even though that carbon's pretty positive, as far as the molecule looks like, to anything else that comes up on the outside, it sees some negative here. What about over here? No, it still sees some negative there. That molecule looks the same from both sides. There's not a pole here. And so we see a difference here in the terms of a bond polarity, where CO absolutely is polar, and a molecular polarity, where the molecule overall does not appear to be different on one side versus the other. Your bond polarities can cancel. What we're really seeing here is a big push to the right, but then we're also then seeing a big push to the left. The net result is I ended up right where I started. The sizes of those are the same. It's a double bond oxygen to a carbon. If your bond polarities cancel, then your molecular polarity doesn't exist. And so this is why shape is important. If we'd had a carbon that was like this, well, I'd have a very big bond out go this way, but then I'd also go up, and it would have looked like I'd kind of traveled the sum of the two. In fact, if you do vector math, that's literally what we do. We just draw the arrow going one way, and then from there draw my next arrow, and end point versus start point shows me my real dipole for the molecule. If I'd shown it as a right angle, it would have looked like it had a dipole. There'd be a bunch of partial negative from these oxygens, and my partial positive would be exposed on the backside. But because the real geometry is linear, we don't have that. This comes up for things like CH4. If I look at CH4, hydrogen up, hydrogen, hydrogen, hydrogen. All these bonds are nonpolar, and so the molecule is also nonpolar. So the bond polarity was nonpolar, and the molecular polarity is also nonpolar. But let's swap one of those carbons out for chlorine, or fluorine. Let's do fluorine. CH3F. Well, I have a carbon. Let's do the fluorine up, hydrogen over, hydrogen out, hydrogen away. Well, I do have a polar bond. We often draw a polar bond in a molecule like this, an arrow pointing towards the more electronegative, a little bit of a plus sign on the more positive side. So I expect some partial negative out here, some partial positive here. Well, this is CH3F. We said earlier, these have bond polarities. This is absolutely a polar molecule. So my bond polarity was polar. My molecular polarity is polar. Keep going with it. CH2F2. I have a carbon to a fluorine, to a fluorine, to a hydrogen, to a hydrogen. In this case, I still have bond polarity. So I go up, but I also go down and to the right a little bit. Net effect is they didn't perfectly cancel. From my start point to my end point, there is a path. My real polarity runs right in the middle of them. Anything that came up to this molecule, because both fluorines are partially negative, it kind of sees one half that looks partially negative, and the other side well, is not partially negative. It isn't as positive over by those hydrogens. I mean, the carbon is partially positive, but when it comes up from the hydrogen side, it does see something different than it saw on the fluorine side. And so this does have a difference in charge. This is a polar molecule. So the bond polarities, there's definitely some polars. And my molecular polarity is also polar still. Keep doing this. CHF3. Carbon, fluorine up, fluorine over, fluorine out at us, hydrogen away. So in this case, I've got bond polarities still. I go up, I go down and over, and oddly enough, I come out at us and back a little bit, leaving my net result being from my center, I come out a little bit. I'm effectively coming between the three fluorines. It's a little hard to show here, but if I have a triangle, it's coming dead out of the center of them. So here's a fluorine, here's a fluorine, here's a fluorine. It's coming straight towards us right here. I still have a polarity. And so I have my bond polarity. Yeah, there's still plenty of bond polarity. And my molecular polarity. Yep, overall, this molecule is still polar. My final CF4, carbon, fluorine, 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 and fluorine. Well, in this case, my in and out cancel. So the going away and coming towards us, they're both moving this way. So one of these is going away and to the left. One of these is coming out and to the left. The net result is I'm still in the plane. I'm neither in nor out, but I have moved left. But now as I go from here and I start applying, hey, let's do my other ones. Well, my up is going to cancel my down, and then my my going to the right is going to bring me back to where I started. Effectively, since these are all the same angles apart from each other, they're all pulling. Well, if you ever have something get pulled in all directions equally, it doesn't go anywhere. This is nonpolar. Despite that I have plenty of bond polarity, my molecular polarity is nonpolar. So for a while, adding more fluorines just continued to be polar. In fact, it got a little bit more polar as we added more. But as soon as we add that fourth, because that fourth is canceling out the other's directions, it goes to nonpolar. This is why geometry is vitally important for us. If we'd drawn Lewis structures without geometry here, for CH2F2, well, depending on how you drew it, you might have thought it did or didn't have polarity. If we drew it like this, it would look like there's a pole right between the two. But if we drew it like this, it would look like they cancel each other out. Lewis structures without VSEPR applied don't let us see what the bond polarity is. We have to apply the VSEPR theory to then look at the geometry and figure out whether we still have a polar molecule. So we have to tie the two together in order to investigate polarity of a molecule.